Okay, thanks for the introduction. And good morning, folks. I'm Qifan Huang from the Institute of Software, a Chinese Academy of Sciences. And it's my honor to introduce the efficient formal verification framework for QEC programs to you. Okay. So we are undergoing an era where quantum computers are flourishing. So specifically, we utilize qubits as the fundamental computing units, which can be in superposition states and to achieve the speed up and reduce the base overhead. And there are currently several technical roadmaps to realize those physical qubits, such as superconducting, trapped ions, and the neutral atoms. And they have made advances in both the qubit lifespans and scalabilities. However, operations over physical qubits are itself noisy and unreliable, which makes it impossible to directly implement quantum algorithms on those quantum computers. Okay, so that's why we need quantum error correction. So to be accurate, we encode many noisy physical qubits into a code space to form logical qubits, which yields a much lower error rate. And there have been experiments over several hardware platforms to demonstrate the power of the quantum error correction. For example, Google's surface code experiment. The figure here shows the construction of codes in this experiment and its ability to exponentially suppress logical error rates with increase of the code distances. So here comes the question. And the critical challenge for QEC is that qubits suffer from not only bit flip errors, but also phase flip errors. So here comes the question. How to design a QEC code that cracks all of the errors? And to this end, we introduce the notion of stabilizer code. Assume that the errors are all Pauli-based errors, and the single qubit error channel is the depolarization channel. So, and the Pauli strings are tensor products of Paulis with phases, and the Pauli groups contains all of the n-qubit Pauli strings. Okay, so the stabilizer is thus a subgroup S from the Pauli group Gn with a constraint -I nothing S, and the code words are all of the vectors in the subspace stabilized by S. So it means the common +1 eigenspace of the elements in S. So, and we thus can protect the qubits by ensuring that the encoded state stay in the code space. And for example, the code space corresponding to the stabilizer generators Z1, Z2, and Z2, Z3 is the span of 000 and 111 state. Okay, so let's take a look at a simple example, the 713 Stini code, which encodes 7 physical qubits into a logical qubit by projecting the initial state 0 and 1 into the code space using the following stabilizer generators. And the distance is 3, so it can detect and correct all of the single qubit Pauli errors. And besides, the Stini code itself is a self-dual CSS code by construction. So it is convenient to implement fault-tolerant logical Qifan gates over it, which we call transversal logical Qifan gates. And now we are going to consider the description of error correction procedures and logical operations. So one high-level way to describe this is via imperative quantum programs. And here we adopt a classical quantum program language and implement the error correction procedures and the logical operations. And this table illustrates the program implementations of the transversal logical Qifan gates and a error correction block building upon the Stini code. And we decompose the QEC block into 5 steps. The first, the logical operation, then the error injection procedure, followed by the syndrome measurements and the external decoder code, and finally the recovery operations. Okay, so the critical problem is how to verify that a QEC protocol has been correctly implemented following this program implementation. And there are indeed several approaches, like performing numerical simulations with tools such as STEAM, or using other verification techniques such as symbolic execution and program logic. In this work, we apply the Hoare-style program logic to be explicit. We use the Hoare triple PSQ. We construct the specifications P and Q using about the program state in a mathematical way and reason about the precondition and postconditions. And there are indeed works that pave the way for using the program logic to reason about QEC programs. And the critical idea is to emphasize the function of stabilizers in both assertions and the programs. However, besides this important inspiration, there are still challenges that prevent the birth of an efficient verification framework for QEC programs. So, the challenges we face can be broadly categorized into two aspects. First, there are still lacks of the program logic that supports the backward reasoning, without which the completeness of the classical assignment cannot be ensured. And on the other hand, how to deal with the hybrid classical quantum verification condition still remains the open problem. So to efficiently tackle these challenges, we proposed a verification framework for QEC programs. We first designed a novel assertion language which possesses concrete syntax and established a sound proof system for QEC programs. And second, we show how to handle the verification condition efficiently. And finally, we implement a practical tool consisting of two modules. We first formalized the program logic and the proof system in Coq, prove the soundness of the proof system, and then implement a automated verifier for QEC programs with the aid of the SMT solvers. Okay, that's all for the background, and let's get down to the business. So I'll first show you how to design the program, the assertion logic. So first, we extended the integer array with the square root of 2 and extended the concept of polystrings into to form the Pauli expressions shown here, PEXP. Okay, so notice that the T gate will transform the polystring into the sum of two polystrings, and thus we introduced the additive predicate P1 plus P2 to represent such expressions. Okay, the definition indicates that the PEXP is indeed closed under Clifford plus T operations. And next, we adopt the Boolean and the Pauli expressions at the atomic propositions and use logical connectives to construct the assertion language. We further interpret those assertions as subspaces of a Hilbert space and do a pointwise lifting from quantum logic for other logic connectives such as and or implications. And you can see that the semantics of Pauli expression P precisely align with those of stabilizer codes, just a modest extension to include the additive predicates. And below is an example shows the expressive power of using quantum logic as a base logic. This is a simple measure in a recovery program. So it says that any state initialized in the eigenstate of +1 in the first qubit will be projected into the eigenspace of D2 upon measurement, and then return to +1 eigenspace of D2 upon recovery. Okay, therefore the whole triple here is correct. However, derivation and the measure and case rule tells us that the weakest precondition will be A0 and A1. Okay, if we interpret the OR symbol here at the classical disjunction, then the weakest precondition, the semantics of weakest precondition is just the set of the eigenvectors +0 or +1, but not the span of them, so which induces an error. Okay, then let's move on to the program logic. Our programming language is a subset of classical quantum programming languages, in which we put the restrictions over unitary operations, but still being able to express all possible quantum operations. And we designed a proof system where we perform direct substitutions of the terms in the predicates. And among the rules in proof system, we specifically designed some of them, making it sound and convenient to implement. For example, for the qubit reset operations, we find that it is equivalent to first measure the Z operators and then perform X recovery if the theorem got flipped. And for two qubit unities, we construct a substitution over elementary Pauli expressions as shown below. And we have proved the soundness of this proof system through both manual derivations and formalizations in Coq. Okay, to further reason about QEC programs, we need to model possible occurring errors in the program. So therefore, we introduce a syntax sugar to replace the condition rule. If B, then U operates on QI else skip. The advantage of using this syntax sugar is that we can greatly simplify the if rule in case of Pauli operators. The inference rule for this syntax sugar is presented as follows. And besides, we also include the for loop as a syntax sugar for program synthesis. The example shows that how to use the inference rule to derive the precondition starting from postcondition. We could see that the conditional Pauli operators just will only change the faces of the stabilizer generators, thus giving us an inspiration to simplify the verification conditions, as I will introduce in the next part. So next part is about how to deal with the verification condition. So first, you need to notice that when verifying a crystal formula shaped like PSQ, you have to first using the inference rules to derive the Wiki precondition P prime, and try to prove that P entails P prime. That is called the logical formula P entails P prime is the verification condition will have to be dealt with. Yeah, and generally speaking, the verification condition P entails P prime is hybrid classical in the quantum, making it difficult to determine whether it is correct. So it is hard to check whether such a verification condition suffices. But for QEC programs, we can push things a little bit forward by noticing that for QEC programs, the verification condition have a common form shaped like this. So let's give a little bit insight into this verification condition. Okay, in the left-hand side, PC is a classical assertion modeling the properties of errors. And errors may change both the form of the Pauli expressions and their faces. So therefore yielding the alternated stabilizer generators GI prime and the logical operators the LJ prime. So to simplify the verification condition and determine whether it is correct, we have to analyze the commuting properties of the stabilizer generators and the logical operators GI and LJ and GI prime and LJ prime. So let's do a case analysis. So first, we deal with the case where all of the Pauli expressions commute with each other. In this case, the classical quantum verification condition could be directly reduced to a classical assertion, which can be solved by an SMT solver. If all the operators in the right-hand side is included in the left-hand side, then the assertions are quite simple, just shaped like this. And for the general case, by noticing that on the right-hand side, GI prime and LJ prime are the products of the elements in the left-hand side. We can use P and Q equals P and PQ to reformulate the left-hand side of VC and reduce to case 1 and find the correspondence of phases. And we provide a theorem to guarantee that. When handling common QEC programs, this is typically the scenario we encounter, since Pauli errors will not change the Pauli expressions, but only alternate the phases. However, we hope that the logic we design can be applied to broader scenarios, including non-Clifford gates, which leads to some non-commuting terms between both sides of the verification condition. When there exists such non-commuting terms, we provide a heuristic to help eliminate terms in the right-hand side, which do not commute with terms in the left-hand side, by utilizing the fact that P and Q and P and neg Q equals P for commuting PQ operators. And now we can return to the example of the Stinney code to illustrate how our verification framework can be applied to verify its programs. We can write down a correctness formula for the precondition initialized in the logical state plus or logical state minus, indicated by a Boolean B, indicated by a phase of Boolean B. Okay, so in the left-hand side, the first constraint limits the total number of errors, including the errors occurring after this logical operation and the propagated errors. And the second term and the right-hand side indicates the expected logical state. And we divided the program into several segments and provided the precondition derived as the derivation passes through each segment. So the Q0 through Q3. And we will skip these detailed parts. And for more details, you can refer to our paper. So combining the precondition in the whole triple and the one we obtain by derivation, we generate the following precondition. Here, actually, no stabilizer changes. So immediately, we obtain the equivalent classical logical formula like this. So that can be verified using the SMT solvers. Okay, And in the last part, I will introduce the tools we implement for efficient verification QEC programs. This figure briefly summarizes the overall structure of the verification framework. We first formalize our theory in a cock-proof assistant based on the library cock-q. And another automated verifier, Veri-QEC, is developed in Python, and we demonstrate its efficiency and the functionality by performing different verification tasks. Okay. And both modules of the tool has been made open source. Okay. In a verified QEC verifier in cock, we formalize the semantics of the CQ programming language and prove the soundness of the proof system using about 4,700 lines of cock code based on the cock-q. We apply this verifier to prove the correctness of a parameterized repetition code program, where the number of qubits in the code distance is parameterized as 2k plus 1 for any positive integer k. And based on the guarantees of the proof system, we implement an automated verifier for QEC programs in Python named Veri-QEC. It accepts the user provided information, includes the program implementation, the code info, and some simple constraint on errors, and then generate the correctness formula and pass it to AST. Then applies the series to generate the verification condition, further simplified into a classical assertion. And at last, an external SMT solver is invoked to solve the encoded logic formula. And we first enumerate parts of the variables and then parallelize the subtasks generated by enumeration to provide speed up to the solver. Okay, so the evaluation shows that Veri-QEC could do full verification on service code with 121 qubits, distance that equal 11 within approximately 3.5 hours, thanks to the acceleration. And we further allow users to add some constraints to errors, such as discreteness constraint, which set the maximum limit for the number of errors in each region, and thus lifting the scale to about 360 qubits. And we provide a benchmark of 14 verified QEC codes. We select the representative QEC code from each code family, like QRD-PC code such as QRD-PC codes, service codes, and compare hard codes we can implement for tolerant logical T-gate with low overhead. Okay. And at last, we provide a comparison regarding functionalities of the verification tools for QEC programs. We summarized the functionalities and scenarios covered by these tools in the table. Okay, at last, let's talk about the future directions and takeaway messages. At first, the completeness issues of the proof system is still open problem. And second, this verification framework has the potential to verify certain fault-tolerant protocols. And finally, incorporating SMT solvers into proof assistance to make an automated and verified verifier may also be a direction that is worth exploring. Okay. The last take-home message is that quantum Hall logic can indeed be practical with concrete assertion languages. And that's all for today's talk. If you are interested in our work, please don't forget to try Veri-QEC yourselves and discover interesting features. Thanks for listening, and questions are welcome.
All right, we have time for a few quick questions. So, well, I'm going to jump in first. So it's interesting that you built two different tools, a Coq tool and a Python tool. Did you try using like Coq SMT or some SMT integration into Coq and see whether that could give you similar performance, or was there some other obstacle?
Yeah, in the development period, we didn't consider incorporating SMT solvers and Coq together for example, using tools like Microsoft F-star. But after the review procedure, we find that it is possible to incorporate the SMT solver into Coq, and we are currently exploring this direction, and this is listed as the future work.
Okay, cool. We have a question in the back.
Hi, I'm Christine Riscala from the University of Melbourne.
Okay.
Thank you for your talk. I was curious also about SMT and ROC. So if you've formalized stuff in Rock is a little bit unclear to me. What's verified in Rock versus what's proven using SMT solvers.
Okay, it seems a little bit unclear to me. So, is the tool you mentioned a proof system which incorporates SMT solver?
The Coq theorem prover?
Yeah.
Yeah, versus SMT solvers. Like, what's the
Okay.
What's been done in each of these?
Okay. In my opinion, and in the experiments we have conducted, we find that the Coq proof system is great at verifying some parameterized programs. But the question lies in that in the QEC programs, you have to call the decoders, which is a classical, which is indeed some classical algorithms. For example, the Blossom algorithm, for decoding for MWQ decoders. And the main obstacle here is to explicitly write down the form of decoders for the Coq proof system. So for this reason, we only verified the parameterized repetition code programs, with which we can explicitly write down the form of decoders. Okay, so and in the automated verifier, we use SMT solvers and provide constraints instead of the explicit form of decoders. Okay, and that's the reason why we choose to use the SMT solvers instead of the directly employ the Coq proof assistant. Yeah.
Okay, let's thank our speaker again.